So hi everyone, thanks for coming. As was mentioned, this workshop is about how to build an industry classifier. We're going to go over a whole bunch of tools that are needed to build this thing from end to end. They are mentioned here: Scrapy, BERT, PyTorch, and finally SageMaker. So a little bit of context before I dive in about BlueVine, where I work. We're a FinTech startup based in Redwood City in California. We provide working capital, which is basically loans to small and medium-sized businesses. We've just launched a new virtual banking product as well. We've funded over $2 billion to date. And the DS team, our mission is quite clear. We want to automate, scale, and improve all of the foundational underwriting decisions that happen in the background. And a little bit about me was already mentioned. I'm a data science manager at BlueVine. I lead the team there. We're about 20 people doing data science or data engineering across the company, both in Redwood City and Tel Aviv. Our team's focus is risk and fraud, financial strength, and marketing. My personal interests are unstructured data and DS infrastructure. So this talk is really at the intersection of those two. You can find the slides on my personal GitHub, so you don't need to be taking photos. So why do we even care about industry, right? Why is this even an important thing to predict, to try to figure out? For us, compliance, right? We can't work with a lot of industries: weapons, gambling, many other types. So this is a key data point for us, especially when you consider automation. Also for portfolio management, we definitely want to be limiting our exposure to risky sectors or just generally balance it out. And obviously, we want to be able to make the smartest decision possible when making underwriting calls. For some very key metrics like income or credit score, it really depends what your industry is to see what is normal, abnormal. So in this example, if we're looking at the distribution of income across a specific industry, we can measure it, we can try to model it using MLE, and then if we see a single data point, we can try to place it on that distribution and sort of say, okay, is this normal, is this not normal, is it especially low, especially high? If we look at the same data point across two different industries, things can look vastly different. Something that looks maybe a little bit skewed from normal on a totally different industry might seem very, very bad. So this is one of our main motivations of why we're putting so much effort into figuring out our client's industry. So this presentation is basically how we solved our business need, right? A client comes in, we need to predict their industry. In our case, it can be one of 135 categories. They are unsurprising, electrician, marketing, steel manufacturing. But when you get to the scale of 135, sometimes they can be very weird. There's maybe 5 types of steel manufacturing or 3 types of marketing. And the big problem here is traditional sources are not good. I don't know who here has experience with trying to figure this out without asking the client, but the sources are just not good. They're pricey, they're inaccurate, and it's hard to obtain them. So our solution for this is to try to infer the industry from the business's website. And the key motivation here is that this is very widely available, and there's no inherent cost in accessing the website, except infrastructure costs, which are negligible compared to the other sources. So our main challenges here are, somehow, if we're going to build a model on this, we need to get a high quality sample. And to get that sample, we need to crawl a lot of websites. So the crawling mechanism has to be efficient, both for the training part and especially for the production deployment part. This is unstructured text, so we need a strong NLP model to consume all of this and predict something good. Because if it's not good, this whole exercise is kind of pointless. And at the end, if we're going to be deploying this, the entire pipeline needs to be scalable. And if we're data scientists who are building this, we care about our independence here, right? If we're going to be using tools to implement this, we want data scientists to be able to use all of the tools and not just be handing it off in the middle. So we did do all this, and the main tools, I've already mentioned them: Scrapy and Scrapy for sort of enterprise scale scraping, PyTorch for writing the actual NLP model, BERT for the sort of NLP underpinnings of it. This is going to be a transfer learning model, and Amazon SageMaker for training and deploying. So what does the pipeline look like from a very high level? We have a client coming in, BlueVine's homepage. They will be entering their details there. So we will be grabbing the business name and the website, usually from a database. In our case, it's a Postgres database. From that point, a crawler needs to spin up and crawl that website. So for us, it's scraped wrapping around scrapey. And I'll talk in detail about all these steps soon. So that's an API and a spider. There has to be some transformation going on in there. The data coming in from the crawl can't be just fed into a model blindly. So we're using Scrapey to do some of that transformations and some of our own custom code, just vanilla Python. Eventually, this gets fed into a model, our amazing model that we have already trained. This is based on BERT, a transfer learning model based on BERT, and using PyTorch. Eventually, all that has to yield a prediction, and we're using SageMaker to create an endpoint around that model. Okay, now I do want to show a live example, and this is always dangerous in presentations. So I have a backup, but let's see if this works. So what you're seeing here is a full run of this model as it's deployed. Basically, I have to tell it what the scraped server is. I have to tell it where to look for stuff or where to put stuff in S3. I have to tell it what the SageMaker endpoint is. Oh, yeah. This better? Okay. Now the website I'm going to be using for this test is some construction website. You can see it here very clearly, a construction website. And if you go into their What We Do page, they actually do say that they are largest general contractor in the country. So let's see if this works. Now it should be crawling. This usually takes about 10-15 seconds. Can you see it? Okay. I will soon know if this works. There we go. It put it in S3, then it's pulling the results from S3. It then sent the entire data set to SageMaker, and it was done. And what do we get back? This lovely little bar plot of the top 3 industries. It hit on it, right? General contractors, about 45%. It does think there's some likelihood of this being non-residential building construction or heavy and civil construction. And this shows you a bit of the problem when building such a model. I expect all 3 of these are somewhat make sense, right? Companies don't do just one single thing. So when we actually use this model in production, we always take the top 3 into account. And I'll talk about this in more detail. But this is actually the entire pipeline, right? This thing is working. Okay. So what am I going to talk about in these 80 or so minutes left? I'll start with the target, right? How did we even gather websites for this model, and how did we tag them? Because there's no way we could build a model without these. Once we had those in hand, I'll talk about how we actually generated the data for the model, right? That's just the target. We had to build a crawler. We had to crawl a very large amount of websites, and it needed not to take forever. Then the model, right? How we designed it using BERT, how we trained it, how we deployed it. And then I will conclude just by summarizing the main points and what my key takeaways are from this. So about the target, right? We had to gather a lot of websites, and we had a bunch of sources that we considered. The first one was our internal data. So if a client comes in and they tell us, okay, this is my website and this is my industry, that helps. But the problem here is that it's just not big enough. We don't have millions and millions of clients, and that is the scale. We need it at least in the scale of tens of thousands, and that's not our scale yet. So this is not very big. And also, it's kind of skewed. If we have 135 industries, it's not very likely we'll get a balanced sample just from looking at who signs up with us. Another option was searching the web, right? Just making these quite naive searches of give me all the car dealerships in the US. And then presumably what you get is websites of car dealerships. The problem here is this is quite high effort. Every time you switch an industry, the search changes, the kind of results you get change. And even this is quite limited. Maybe you can find car dealerships, but you're not going to find too many, I don't know, fabricated plastic manufacturers this way. And the third one was just proprietary databases. This means buying data. So we went around various vendors, and we were asking, give us website data with some sort of information about what the industry is. So the good thing about this is it's big. It's finally something big. The problem is that it's pricey and many times outdated. So you're getting many websites that are just dead. So we eventually used all of these, right? We used all of these sources and basically hoped that they would make up for the failings of one another. So we have 135 industries, and we want somehow the sample to be balanced. But in order to balance it, we need to know the industry. But if we knew the industry, we would need a model, right? If we had the ability to say what the industry is based on a website, this entire exercise would not be necessary. So we had to figure out what kind of proxy we could use for each data source. For our own BlueVine data, we were actually using what the users told us they were doing, which is surprisingly inaccurate, just so you know. In the web searches, we were using the search term. If we were looking for car dealerships, then anything we got back would be a car dealership. And the proprietary data, we had something called a NAICS code. Now, I don't know how many people are from the US, but this is sort of the standardized way of classifying industries. And it has some pros, some cons. It is quite old too. So we had to do something. We used these, and we basically just hoped for the best, right? We sort of balanced it according to this. And our thinking was, when we get it back, it should be somewhat balanced, if not perfectly. So our goals, given this data set, were to get quality tags. It had to be in a reasonable time frame. And we had to stay within budget, right? We're not a giant corporation with just infinite amount of money to spend on this. And we did crowdsource the problem, right? We collected about 250,000 websites, and we looked for a vendor to do this. So doing this via crowdsourcing is hard. Crowdsourcing tasks are usually very simple, very sort of confined tasks that you can do in like a few seconds. And here, a person doing this would have to understand all of the 135 industries that we defined. And they would also have to understand what a business does based on the website. And they would also have to make a call which one to pick if a number makes sense, right? You've already seen, looking at a construction website, if you have 10 different construction categories, sometimes it's really hard to tie break between a few. So we actually had to put in a lot of work here, because if there's the famous adage of garbage in, garbage out. If we were not doing this part right, everything else would just be worthless. So what we did, we tried a bunch of strategies, and we let vendors try those strategies out and sort of, compete with each other on it. So one strategy was to break up the tasks into smaller parts. But the problem here is that if we have one observation, it's suddenly not just one decision being made on it, it's multiple decisions. If you decide first if this is construction or finance, and then what type of construction it is, you're paying twice for that decision. So this had a problem, budget-wise. One other strategy is to get just multiple judgment for every observation, and then hope that the distribution somehow centers on the right decision. A problem here is, again, the money part, right? You're paying for now 5, 10, 15 observations decisions per single observation. And we found that sometimes it doesn't matter if you're asking 15 people. If nobody knows the right answer, it's still going to look bad. It doesn't help to get 15 bad answers. And the third strategy was to actually train a team and hope that after you train them for a while, they're able to make a smart and informed complex decision. The problems here are that it's quite slow, and when you slow things down in crowdsourcing, you're inevitably paying more, the same way you're paying when you're increasing the number of observations. So we set a budget limit. We set a maximum type per task that we were willing to incur. We actually developed a small tagged set in-house, so we had a few people work on this for a few days and give us a few thousand, just as a baseline. And we held vendor trials for all these strategies. We basically picked the vendor that was under our maximum time cap and gave us the best accuracy. And that happened to be a vendor called Cloud Factory, so I'm giving them a little shout out here. I don't know which of you knows them, but they're pretty great. So the outcome was that this took us about 3 months to do through Cloud Factory. So it was 250,000 websites, and it was not balanced, but it was good enough. And by good enough, I mean there was no industry that was so severely underrepresented that we could not run a model on it. So it was a good outcome for us. Okay, so now we have the tags down. How did we get the actual data? So we built a crawler. For every URL, we're going to need The homepage text, ideally cleaned in some way, right? At least for this model, we were not looking at the HTML tags, but it's totally doable to look at them. We also wanted to go deep inside the domain, right? We didn't want just the homepage. We wanted to be crawling internal pages as well. We want to pick up some metadata, maybe the path, the title, the click text. And we also want some discretion into what the crawler is doing. Out of the box, crawlers usually go into links as they encounter them. And there is some correlation between the order and the importance. But it's not what a person does. If a person goes into a website, they don't just randomly click links the first time they see them. So we wanted some discretion there. And we also wanted to be able to save everything as a backup, because if we're spending a week crawling 250,000 websites and then we're missing a comma somewhere, we don't want to crawl everything again. So our tool for this was Scrapy. It's basically a fast and high-level web crawling and web scraping framework. I highly recommend it. There's a bit of a learning curve there, but it is worth it. About Scrapy, also very high level. What it basically does, it takes a URL and it makes a request off of that single URL. It will obtain the response back, and that response you store in something called an item. And this is basically like a dictionary, a key value store. You take from the response bits and pieces that you care about, you stick them in this item, you send the item into something called a pipeline, which is where you decide how you save this thing, right? Up until now, it's just sitting in your machine. You do have to put it somewhere. So the pipeline shuffles it off to the storage. While this is happening, if you want to be crawling internal links, you're also pulling internal links from that initial response. And then every link inside there just loops back, right? It becomes a URL and goes through the entire pipeline. OK. Now, I'm not going to run this, but I'm going to show you one that already ran. Can you see this? Good. So this is that same site, the construction website. Scrapy also has a nice Python SDK that you can use to interact with it. Most people use just the command line, but because I wanted to show it here, I do need this package. There's a little execute. I don't think it matters too much. It's just a command line to tell a specific spider to go ahead and crawl the website. And I wanted to show you how our spiders were extracting data. So you see a little table here where the input URL is the domain. We're recording the URL order, in what order we encountered it. We're recording the specific path that we crawled. The ranking, which I'm going to talk about, it's not maybe very clear why it's 1, 2, and 100, but I will touch upon this. We're looking at the response text, at the title. So the entire crawler was basically intended to output this data frame, right? This already looks like something that is, workable in terms of sticking it into a model. It's not just a mass of text. A little bit of zoom in. This is what the non-HTML text looks like from one of the pages. So this is like what a person would be reading if they were entering the website. And this is what is fed into the model in some sense, right? This kind of text. OK. So this is what a very standard Scrapy project might look like. If you go into the Scrapy website and download the tutorial, it will start you off with something that looks very much like this. In the spiders directory, you put your crawl logic. In the items script, you decide what you're going to be extracting from every response. The pipelines, how you're going to be saving. And there's various settings to define how Scrapy will be working. There's so many settings. So it really depends what your use case is. I'm going to dive a bit into how this works. Like I said, there's a learning curve. I hope I can make the introduction painless. When you define a spider, you're basically defining a class that is a subclass of Scrapy's generic spider class. The most important thing you have to be putting in there is an argument for the URLs that you're going to start with. This would presumably be a list of all the domains you want to crawl inside this spider. What we did, well, the first thing you do is you have to pass this as a string. So you split it up into a list. And we also added a counter. Because we want to be limiting how many pages we're crawling inside each domain, we actually have to count how many we've already crawled. So this is a little custom thing that we added. Just a count of how many links we've encountered per specific domain. The start request method is what actually does the first request for each of these URLs. So you have to implement that. And the parse method is for each one of these responses, what are you actually going to be doing with, for each of the requests, what are you going to be doing with the response? How are you going to be extracting data? And if you're going to be following links, that logic happens there as well. So let's dive into the start request method. Basically, it's a loop, right? You're looping over each one of the URLs that you sent in, and you're making a request for each one of them. Notice that already in the request, we're telling it which function is going to be handling the response part of this. And that's the parse method that we'll look at in a minute. This part, we discovered while we were working with this. There is no native way to send information, across this entire loop. Well, there's a native way, this one, but it's not super clear. The one thing that we want to be sending through is that count part, right? What you're seeing here in the URL rank, that is us counting how many URLs we've seen per domain. So each first URL gets the rank of 1, and you'll see later where it actually updates. So this is just a way of attaching data from one method to another. So in the parse method, the very first things that happen is the response that comes back, you want to make an item from that response, right? That is just storing bits and pieces in a dictionary. After you've made that item, you want to be following external links. So there's a little function that just extracts those links. And then there's a loop, right? For every link in the links, make sure you have not exceeded your max links per domain. If you have, then break. If not, then you go ahead and make another request. Now let's follow these. This is the make item method. I don't want to talk about this too much. I'm basically saving many things. The most important thing is the response text and the URL title. This is where we're also cleaning the text from HTML. This is very flexible. You can make it be whatever you want. And there's also this part here. This is where we update the counter, right? After the responses come in, we already know we've gotten an answer for this website. We know what URL it is associated with, and we're able to update that dictionary. And you can see it's part of that meta object that travels with the request and the response all through the pipeline. Inside the extract links method, remember I mentioned that we care about sorting these internal links. We want to be entering specific ones, especially if we're limiting to a low number of websites per domain. We capped it at 5 for this model. So we don't want to be missing out on important pages if they happen to be 6 or 7. So there's a little sorting going on here, and it's nothing fancy. Basically, we asked our analysts what pages they were looking at when they were entering a website, right? How did they know where to navigate to save time? So they gave us a bunch of keywords, right? We tried to find the About Us page, the Story page, if they have anything describing their services or capabilities, what they sell, what they do, where they are. So we put all those into really just a keyword search. If any of these keywords appear in the text or in the title, in the URL text or in the URL itself, then we would push those up in the order in the hopes that at the very least we would not be missing out these pages when we're capping at 5. Okay, so we've made our item and we've already followed the internal links. I did skip over this little thing where it actually returns the item, right? The parse method is supposed to be shuffling off items to that pipeline thing that is supposed to be storing them. And that happens here. So the item is sent to the pipeline after it is stored. And what does the pipeline do? In our case, something very simple. It just collects all the items it gets, right? Collect them in a list. That's it. The scraping process is finished, presumably after encountering at least 5 internal links. And then the pipeline has collected about 5 items, and the spider is going to close. It's done its job. Then the pipeline just has to decide how it's going to store these 5 items. So we have functions that turn it into that data frame that I showed you before, that nice little organized thing. We do it separately for the clean data, for the raw data, just for backup purposes. And then we stick it into S3. That's it. That's the entire pipeline. So that data frame that you saw would make its way to S3 as a JSON. Okay, so that was how to crawl presumably one website. A spider, it can do more, but it was an example to show one website. We have 250,000 websites. And we want to get this done, fast, or at least in a reasonable time frame. So we want something that can run in batches. We want it to be able to run in parallel. We want this thing to be always up. We don't want something running on somebody's laptop, and if they drop the laptop or something spills on it, then the thing is dead. And ideally, there would be some logging or UI that makes it somewhat user-friendly and not a horrible bash script. So our tool for this was scraped, and it's a service for running Scrapy spiders. Basically, it packages your Scrapy project in some way, and it deploys it in its internal sort of server mechanism, and then you can interact with it as an API. It's built obviously for Scrapy. Very cool tool, very simple to use. I'm not going to go too deep into it. It also has tons and tons of settings. The important settings are whatever you tell it in terms of how aggressive to be when you want to do the parallel crawl. And you obviously need to define your port if you're going to be interacting with its UI. Running it is actually really, really easy. If you've put it in the same directory as your spider project, all you have to do is type scraped to start the service, and scraped deploy to deploy that spider that's in there. Literally, that's it. Once you've done those two things, you already have a server that you're able to interact with that can parallelize the entire thing. Just 2 lines. I'm going to show a little example of how to interact with scraped. This specific example uses the scraped SDK for Python, but there's obviously many ways to do this. So import it, put a whole bunch of settings, what your host is, what the spider name is, what the project is. These are all out of the box things. And then you construct your API, you load presumably a very big list of URLs, you split it into chunks, in this example, chunks of 100. Then you have to define some parameters, right? How many of these do you want running at the same time? How many of these do you want to be queued? What's your polling interval, right? How many times are you checking the server status? And then you start looping, right? As long as you have something to run on, check the server status, see how many are running, see how many are pending. Do some break clause, right? If you've already exceeded your bounds, then don't do any more. Otherwise, just schedule that job. Send over that URL batch, and scraped will handle spinning up the spider, running it in a loop, and going through the entire thing of a pipeline and sticking it in S3. Okay. So after that step, presumably we have crawled 250,000 websites. We have all of their data organized in a nice-ish way in S3. A way that is basically that data frame that I showed you. And now we need a model. So our model is using BERT. And I'm not going to talk too much about BERT. It deserves its own 90-minute workshop. I don't know what the level of familiarity here is, but I'm just going to say on a very, very high level, from the perspective of somebody that just needs to use it and not necessarily understand what's going on, BERT was our way of turning a string of text into a vector. Right? That's what we cared about. In this case, a string of text could be the text coming in from the website, right? That big chunk of text that I showed you. So it's a way of vectorizing this. BERT has a standard and a large version. We use the standard version for a dimension of 768. Now, BERT allows a maximum of 512 tokens. And that means tokens is its way of breaking up words. So it is definitely conceivable that a single web page would have more than that, and it's very likely that a website, right, with multiple pages would have more than that. So that's a problem, and I'll talk a bit later about how we dealt with that. But it's a thing to put out there. Now, BERT is open source, and pre-trained models are available for transfer learning, which is what we did. And for PyTorch, there's an excellent package by Hugging Face called Transformers. If anybody's going to be using BERT and PyTorch, I mean, this is a no-brainer. So perhaps a few more words about BERT before we move on to using it. The way it tokenizes is an algorithm called wordpiece. And the good thing about this algorithm, it's very, very robust to the out of vocabulary problem. So it's not going to fail when it, on the concept of seeing something it doesn't know. It does have a limited vocabulary, but it's not going to fail even though it's just not going to happen because of the way it works. But it's a really nice algorithm that you can use in other contexts as well. And BERT uses transformers to perform something called attention. And the gist here is that it can consider the same token in different contexts, which is super important for our task. Because when you're trying to infer, when you're trying to understand something complex like what a business does, it is very conceivable that you will encounter this problem. BERT is bidirectional, so it does not read the text from left to right. It sort of takes it piecemeal. And it is able to achieve state-of-the-art performance on a whole host of NLP tasks. So if you're going to be building an NLP model, that in itself is probably a reason to go to BERT. Okay. On a high level, how does BERT work? The very basic input is a sentence, right? A string. The first thing that happens is the tokenization step using word piece. So the string is now a vector of variable dimensions, right? Depends how many tokens were extracted from the string. Now you do have to do a truncate or pad step because BERT cannot accept more than 512. And once you decide what your cap is, everything needs to be at that exact length. So if the example we're using is 256, you will be adding zeros where you need to, and you will be cutting off where you need to. So now your input string has turned into that vector, and then BERT attaches its embeddings per every token. So now your 256 size vector is a matrix. And then this matrix goes into all of the transformers. Now the BERT version we used has 12 transformers, and each one of these transformers consumes this matrix and spits out its own matrix. So now you have 12 matrices of this size. Now where do these 12 matrices go? BERT has something called a pooler, which basically extracts it takes the last 4 matrices, the matrices of the last 4 transformers, and extracts only a single vector from them, right? You have 256 vectors in one matrix, but it's looking at the vector of the CLS token. Now the CLS token is a thing that you attach at the beginning and end of every vector, and it's supposed to be something that represents the entire semantic context of the string. It's sort of like a catch-all for that. If you want to know more about this, you should definitely read up. But what is in effect happening is that you're actually taking just one vector out of that entire representation. You're not taking any of the vectors that represent any of the specific tokens. So the pooler takes the CLS vector from the last 4 layers, and it basically sums them up. So at the end of all this, you have one vector of size 768. That goes through an activation layer, and finally an output. So this entire pipeline is how BERT will take this one string, which for our examples could be the website text, the single page text, and get one vector. Okay, so that was BERT. So how does our model use it? Our basic idea is, okay, we have a single observation for us is a website, and we were also sticking the business name in there, like as an attachment. We had to organize our data for every observation into a very clear set of inputs, right? It has to be like somehow one item that contains all of the various inputs that we could stick in there. And we have to use BERT to convert all of the free texts into these vectors. And then somehow we have to wrap around it in a model that can spit out 135 industries. So the way we did it, at least the way we have a bunch of versions running. The version I'm going to talk about is the one that uses the first 5 links. I've already mentioned that number. And from those 5 links, we're taking the page text, the title, and the website domain. We're also taking the domain extension, if it's a .com, .edu, .org. And we're also adding the business name on the side. So this is what the model looks like on a high level. This is one of 2 slides. We have 5 page text coming in. We have 5 page titles coming in. We have a domain, we have a business name, and we have the extension. All of these free texts that appear at the top, all of them are fed into the BERT tokenizer, and then they turn into vectors of various sizes via that entire pipeline, right? And all of these vectors, after the tokenizer, are fed into BERT, and then BERT turns them into vectors of 768. So because we have 5 page texts, those turn into 5 vectors. The same goes for 5 page titles, 5 vectors, 1 domain, 1 vector, one business name, one vector, and the extension, because it's just a category, that doesn't figure in there, right? That just turns into a sort of a hot encoding 10-dimension vector. So that's the first part. And all of these use the same single BERT model, right? This is not 5 BERT models. This is one pre-trained model that's doing all of that work. Now, once we have all of these vectors in hand, we basically concatenate them into one giant vector. Nothing fancy. We actually tried a whole bunch of fancy stuff, and this worked the best. One big giant vector of size 768 times 12, because that's how many BERT actions we have, and then that plus 10 for the extensions. All of these go through a dense layer, and this is really the only trainable part of this model. Everything else was pre-trained and just applied as is. This dense layer for categorizing the websites is trainable. We stick it in there. There's a softmax logic to turning it into probabilities, and then you get your final prediction. So what you see here is basically how we dealt with the BERT limitation of 512 tokens. We could not stick 5-page texts into a single BERT model. We could definitely not stick all of these texts into a single BERT model because it would clearly exceed the cap. It might seem trivial when you see it here to just use BERT, on all the smaller pieces, but it took us a while to reach this. We were thinking in the beginning of ways to try to reduce it down to 512 because it wasn't clear that this giant concatenated vector would actually, have meaning that a model can figure out. Luckily, it turned out that it did. So if any of you have such a challenge in the future where you want to be using BERT and your text is longer than its cap, you should definitely try just splitting it up and applying it piecewise. Okay, so now we have this model sort of set up. We used PyTorch, right? That was our tool. So we were going to be training and deploying it with PyTorch. PyTorch is basically NumPy for GPUs. It has this lovely feature of autograd, which makes it relatively easy to debug. For anybody here starting off with building neural networks, I would start with PyTorch just for this. You can actually put breakpoints in areas that make sense, and it's not going to be trying to compile anything. It is actually building your network as the lines are interpreted. Really fun. So what does this cycle look like? This is sort of a combination of the generic neural net training cycle and how PyTorch splits it up into its own logic. So you start with an input batch, something that can comfortably fit in a GPU. Then you calculate the outputs. In PyTorch, it's called the forward method. Then you calculate your loss from the forward method, right? You're comparing your outputs against your labels. You're seeing how they stack up. And then you want to calculate the marginal loss, right? And that's the backwards method. This is the beginning of gradient descent. Then once you've calculated the marginal loss, you want to update the weights based on those losses. In PyTorch, this is the step method. And then you do this loop over and over again until all your batches are done. And then your epoch is done. And then you can do multiple iterations on this based on how many epochs you want to run. In transfer learning, and specifically when doing transfer learning from BERT, you usually don't do more than 5 epochs. I mean, we started seeing degradation after 3. This is the validation cycle, much simpler. You are looping over the test batches this time, not the training batches. You're looping over the batch and then forward, and then calculating the loss. But there's no update happening here, right? You just run through this entire thing, collect all of your losses, and then you have some sort of baseline to see how you performed. Okay, so in order to be able to run this thing, we had to organize the data set in a way that can work with PyTorch. Up until now, we just have data frames, right? We have data frames with some organization, some fields, some columns, and clearly you can't just shove those in there. So we had to convert all of the text elements into numeric vectors. We had to convert everything to tensors and put everything together so that one item somehow contains all of these inputs. We have, I think, 11 different inputs, right? So an item has to contain all of them in a very organized way. And obviously, we have to batch it in a way that can fit inside the memory of a GPU. So we basically wrote a very nice big function for this. I'm gonna talk about parts of it. I mean, it's really too big to talk about all of it. So make data set, right? It gets in an input data frame, which is exactly what you saw, that data frame of crawl data. We specify a whole bunch of settings. We pass the tokenizer, right? That's also a pre-trained object. How many pages we want to run, what length are we going to clip, the page text, the page title, the domains, the business names. We pick those lengths based on the distribution that we saw in the actual data. I think we picked the 95th percentile, right? So 95th percentile of all page titles was 16 tokens. So that's what we picked. We made this function, we built it in a way that could be parallelized because there's really no dependency here. This is just a pre-processing function. So there's a chunk size, there's a number of jobs, and then we could spin this up on, we could run it on a very, very strong server and actually pre-process the entire thing quite fast. So the first method we have here is something that takes the input data and just splits it into pages. If we care about 5 pages, we don't want one giant data frame. We want 5 clear input pieces, page 1, page 2, page 3. And then the important step that happens here is, given those 5 data frames, we want to tokenize and truncate all of the fields that we care about in those data frames. The important ones here being the page text and the page title. So I'm not going to go too deep into this function. You can imagine that there's some sort of loop happening there, going over the different pages, going over the different fields. And the key function, before I step into it, eventually we combine everything into a big giant tensor data set and return it. So going back into this, there's a key function here that handles the tokenization and the truncation of a single sequence or a single sequence of sequences. So we start looping over that, right? This would be maybe if you got a single chunk of URLs and each URL has 5 pages, you maybe have 100 sequences to go through here. So you start looping over them. You use BERT tokenizer to tokenize that sequence text. So what you get back now is not a string, but a list of stringish tokens. Those stringish tokens have to be immediately converted to numbers because you cannot stick them into a model. So the tokenizer does that for you as well, right? You shove those sequences in there, and now what we have is a list of numbers. And this is done via, the internal sort of dictionary representation that the pre-trained tokenizer has. Once you have those IDs, you need to make sure they are all of the exact same length. You need to pad anything that's too short, and you need to truncate anything that's too long. So that's a single function here that does that. In case you have empty strings, we just had to handle that by sticking the two specific tokens that BERT expects to see every time. It expects to see a CLS token and a SEP token. And remember, this CLS token is super important because that's the only actual vector that your pre-trained BERT is going to be looking at, nothing else. Okay, so we are done with this loop that truncates and tokenizes everything. We've stuck everything into a big giant tensor data set, and we have returned it. That is the make data set function. So now you actually have to start the train loop, right? All we've done now is just write a function that organizes the data. So we define exactly which BERT model we want to be using. The one we chose was the cased version, the base version meaning it's only of size 768, and the cased meaning that it cares about upper or lower, right? There's a version that doesn't. So when you tokenize a sequence, a capital letter will tokenize differently than a lowercase letter. You load your pre-trained BERT model, you load your pre-trained tokenizer, and then assuming you've already split your data into train and test, you just apply this method to each one of the data sets, right? This method was written to accept the raw crawl data. So put in raw train data, put in raw test data, get back 2 nice data sets of tensor data sets. Now, we also have to split this up into batches, right? We can't just stick a giant train data set into a single GPU. And PyTorch has a very nice concept of a data loader. Basically, it does just this. You give it a set of you give it a tensor data set, you tell it what batch size you want, and you also have to tell it how you want it to be extracting pieces from it. A random sampler means it's going to be extracting a random 16 data points from your set. A sequential sampler means it's going to be going, batch by batch, first 16, second 16, third 16. Once you've done that, we're basically done, right? We have our train data loader, our test data loader. We have two objects that are ready to yield, nice batches for the loop. So this is this step right here, right? This is the batch input step. We've created our data loaders and we're ready to extract a batch. The next step is applying the model forward function. Model forward, this is where you actually define the graph of your model, right? This is where you say what layers your model is going to have, what transformations you're doing, if you're combining anything, splitting anything. So the entire pipeline that I showed you, it's going to be defined here. You invoke it with all of the inputs that you care about. Those are our 12 or so inputs. And it will eventually calculate your output. In a training mode, it also calculates the loss. So let's step into this. The forward method is defined where you construct your model. So I begin with the construction of the model. We just called it BERT website classifier. It is a subclass of a pre-trained BERT model. And this is an object provided by the Hugging Face package. The reason we did this is we wanted to be able to leverage all of the native methods that they provide, the training methods, the predict methods. And we're also copying their structure. If you step into their GitHub, you can see how they build BERT pre-trained models and then how they build models for transfer learning. We just copied their way of building transfer learning models, and they are subclasses of the pre-trained model. Really instructive for anyone attempting to do this. Check out how they built it. The very first layer in our model is a BERT model, right? We load a pre-trained BERT model, and all of those 12 transformers, that entire pipeline is represented here just as a single layer in our model. And then we have just a second layer, which is a trainable linear layer, right? This is a layer that accepts one giant vector as an input and has to somehow spit out a vector of the number of our labels, which is 135. This is, again, the only trainable part of this model. So we've defined this, and now we have the forward method of that object. The first thing that needs to happen, you need to specify everything that goes in there. So this is all of our inputs, the page text, the titles, the IDs, the business names, the URL extensions. You might see here all these masks. Masks are simply vectors that indicate 1 wherever there's a token and 0 where there isn't. This is something that BERT needs in order to run. I don't want to get too much into this, but it is really that simple. If you have 5 tokens and then 200 zeros, this will have 5 ones and then 200 zeros. So the forward method accepts all of these things. And the way we defined it is exactly the way it was shown in the outline. We stick each one of these vectors into our BERT model. You see self.BERT, that is the pre-trained BERT model. We stick it in there and we get back our vectors, right? This is all that is. So the top 2 are actually single vectors. The bottom 2 are lists which contain 5 vectors, 1 for each page text, 1 for each page title. And eventually we combine them all, right? 12 vectors, turn them into one big giant vector, use torch.cat to make it one big giant tensor. And then that's it, right? That is the output of using pre-trained BERT. All that is left is sticking that output into our trainable layer, which we called Classifier, and then get the output of that. So now logits is just a vector of 135. And in the case of training, you also have to calculate the loss. So you have your labels, you have your outputs. It's both vectors of size 135. You calculate your loss, and you return that as well. So that was the model forward pass. Now, we only defined it in that step, right? We still have not invoked it. So after defining it, we have to instantiate our model. So you see we're using our BERT website classifier class, and this is why we made it a subclass of the Hugging Face transformers. They have a very nice method called FromPretrained. All we have to specify is the type of BERT model we're going to be using, and then it loads it up for us. This line here is if you're going to be using multiple GPUs using PyTorch, you need to know the syntax of how to do it. In PyTorch, it's super easy. All you have to do is wrap around it with nn.dataParallel, and it will, by itself, leverage however many GPUs you happen to have on the instance. So now we need to do the loop. right? We've defined our model. We need to be using our forward method. We start iterating over our epochs. In our case, it's 3 epochs. We set the model to train. And in PyTorch, this just means that the model is allowed to update its weights. We start iterating over all the batches in our train data loader. Every batch is passed to the CPU. And the very first step is just to extract all of the things we've crammed into that batch. Remember, we've crammed in a lot of stuff for every item. So we're extracting the text, the titles, everything. That's step 1. The reason we're doing this is in order to invoke the forward method of the model, we have to pass the inputs at the exact order and the exact place that they need to be in. Because page text are handled differently, page titles are handled differently, the domains and the business names are handled differently. So we extract all of that from the batch just to be able to organize it into the forward method. That's exactly what's happening here. Once the forward method is invoked, you get back the loss and the outputs. So all that was this step, right? Defining your model, defining the forward method, starting a loop over all your batches, invoking the forward method for every batch, getting an output and a loss. Now, the forward method calculated the loss just for one batch. But you want to be able to compute the marginal loss as well, right? The loss with respect to all of the trainable parameters. The way PyTorch does this, it actually updates the grad attribute of the tensors with this. And in order to actually do it, all you have to do is invoke the backward method. So that's what it looks like here, right? You can see this line right under the forward pass. We got our loss and our logits. Because we're using multiple GPUs, we're taking the mean of the losses across multiple GPUs. And then we're just invoking backwards, right? That is it, literally. You tell it loss.backwards. It has now computed the marginal loss with respect to all of the trainable parameters, and you are done with that. Actually, 1 line, 2 lines. The last step is you've already calculated the marginal loss, but you still have not applied it. So you need to update all of the weights based on this insight. In PyTorch, this is the step method. So it will basically update all of the trainable weights based on all of the items that you calculated in the backwards method. We're using the AtomW optimizer. This is really just an out-of-the-box thing. This is the recommended one. Yeah, I'm going to skip over this. We do have to zero out the gradient in PyTorch, because if you don't zero it out, it will be retaining weights from previous batches, and you definitely don't want to do that. And again, 1 line. Right? Optimizer.step will apply all of the marginal losses you've calculated to all of the weights, and that's it. And then you're done with the loop, right? And you're ready to go to the next batch. And you just do this all the way until your data loader is done. So at the end of this step, we've basically trained our model, right? Now we have to somehow deploy it. We have to turn it into something that is hosted in the cloud, ideally something that's always up, and something that we could communicate via an API. And also ideally something that can scale by itself. If we have variable communication spikes, we want it to spin up or spin down according to those needs. So our tool for doing this was Amazon SageMaker. The reason we were using SageMaker is because it gives you all of the pros of Docker deployment without having to write any Docker code. Now, I don't know how many of you as data scientists write Docker code, but this is something that if you can avoid, you want to, right? This is not something that's considered standard in the toolkit of a data scientist. Now, SageMaker supports a bunch of modes. It has a tagging mode, an explore mode, a train, and a deploy mode. I'm going to be talking about just the deploy mode. And it does have that auto-scaling feature that I mentioned, right? Once you deploy a model behind an endpoint, SageMaker can spin instances up or down based on your sort of response or throughput needs. So also from a high level, how does SageMaker work at all? How does it do this magic of allowing you to deploy something without having to write any Docker code? What it starts with is your custom code. right? Custom code and artifacts. If we're talking about a trained model, something they've already done, you have all the code that is needed to apply that model, and you have the objects, your trained model, I don't know, whatever artifacts you need, the model itself, and maybe some supporting files. So the first thing that happens, it's going to zip all of this stuff and put it in S3. Then it's going to build a Docker image. And you have to specify what kind of Docker image you want in a very general level. Is this, a PyTorch Docker image? Is this a TensorFlow Docker image? Is this just your generic Python scikit-learn Docker image? And if you have any specific packages, you put in a requirements, file somewhere, and it will make sure those are on the Docker image as well. So it will build that. It will store that in its Docker repository. It will spin up an EC2 instance. It will pull that Docker image into the EC2 instance, and it will take your model, write an app around it, and give you an endpoint. All of this with actually just a few lines of code, which I will show. But at no point here are you writing any Docker code. There is a local mode here. I'm not going to talk about that, but it's a way of avoiding cloud costs if you want to be testing out your thing. So how does SageMaker understand how to do all this? It's based on the concept of an entry point script. And this script is supposed to be sort of something that you put between SageMaker and your own code. There are a bunch of, it's more like filling out a template, right? You have a bunch of conventions that you need to go by, and then SageMaker is able to leverage those conventions to communicate with your code and accomplish this. So the important thing to know about the SageMaker's entry point script is model.fn and predict.fn. These are two functions that you have to implement just as pointers to your code. Model.fn has to be a pointer to how to load your model. Predict.fn has to be a pointer to how to apply your model. And then SageMaker will be invoking those functions in different contexts. There's a whole section for environment variables, but that's only important when you're trying to debug it. Basically, the important thing to note here is that when you're going to be spinning up an endpoint, SageMaker will be looking for model.fn and predict.fn, and will be invoking those. So what does the entry point script look like for this specific case? This is model.fn, right? This is intended just to initialize a trained model. So what you see here is loading from pre-trained, right? In this case, our model is called just model E, and there's one line to load it. There's another line for loading the tokenizer, and those are the two objects that we need to actually have our model run. We need our own trained model, and we need the pre-trained tokenizer to do the pre-processing step. So model.fn just loads these two pre-trained objects and sends them back. That's it. And these two things are coming from our custom code. And predict.fn, its inputs are going to be what you're going to be predicting on, right? You have your URLs, and you have the crawl data that came back from URLs. So that's going to be the input for predict.fn. It's also going to be getting all of the pre-trained stuff that you got from model.fn. So if you returned a model and a tokenizer, that's what your predict function is going to get as well. And then there's really just one line. You have to write some code on, given your model on one hand and your input data on another hand, you have to write a bit of code on how to combine the two, and then just make sure predict.fn points to this. That is it. In PyTorch, the prediction looks a lot like the training cycle, except that you aren't updating weights. You're still iterating over batches. In this case, those batches would be inferred from the input. You're extracting the outputs from each batch. You're collecting them. You're returning them back. So this was just the definition of the entry point script. We still haven't deployed or predicted anything using SageMaker. We've just written the script that allows that to happen. So how do we actually deploy something using SageMaker? The first thing you have to do is identify yourself, right? Anybody who's familiar with Amazon services, there's a whole authentication step that has to take place. So that's a one-time thing. This is us authenticating with SageMaker. The next step is to make sure you're telling SageMaker which Docker image you want it to be using. In our case, it's a PyTorch model, so we want it to be using a PyTorch Docker image. And then we basically make an item called the PyTorch model, right? And this item has a few bits and pieces, and they are themselves pointers. The first thing we tell it, where is the entry point script, right? That it can use to communicate with our code. Second thing, where are the model artifacts? In this case, that would be our pre-trained model, right? The model that we took all the time to train. We have to stick it somewhere in S3, and then tell SageMaker, this is where it is in S3. This is where you can get it from. because we're using PyTorch, we have to specify the PyTorch version we want to be using. And obviously, because we're using Python, do we want to be using Python 2 or 3? All of these impact what kind of Docker image you're going to be getting. Once you've made this object with these settings, you're ready to deploy. You specify which kind of EC2 instance you want. This specifically is a GPU instance. And then you just call the .deploy method. That's it. Now it's deployed. If you try running this locally, it will take maybe 10 seconds. If you try running it against an actual, EC2 instance, unless your code is very big, like, hard disk space, and you're incurring a lot of time to upload, this should take only a few minutes. For our model, it took, I think, 2.5 minutes. And once it's deployed, you're just going to see it, right? You're going to see that endpoint in the AWS panel, and it's now a cloud service that you can interact with. So all you've done is write a script, which is basically filling out a template. You've set up a bunch of settings called deploy, and now that endpoint is live. If you want to predict against that endpoint, basically you call the .predict method. There's a step here where I tell it should be expecting JSON input. That's not very important. But this is that same object, right? The cloud predictor object, I call .predict, and that's it. That's how you communicate with this endpoint. And you can do that, from any server or machine that can authenticate against it. You can do it locally. You can use it, in a production environment. You can deploy multiple endpoints in many settings. And you can see we haven't done any Docker code anywhere here, right? There's no Docker file. There's nothing. So that's basically it. I want to conclude by sort of summarizing all of the things that we went through. The first thing we did was build a sample of size 250K websites. We employed a whole bunch of search strategies and balancing strategies to try to get that sample to be usable by a model to meet our business needs. We tagged that sample using crowdsourcing, and we tried a whole bunch of strategies there. We crawled all of these things using Scrapy for small scale and Scrapy-D for large scale. Then we built a big NLP model, which is basically one single trainable layer on top of BERT. We found a way to circumvent the 512 limit cap, which was crucial for us, right? It was clear that we were not going to be able to build a good model with just 512 tokens. We then trained that model using multiple GPUs. And we were using pre-trained BERT with PyTorch. And then we deployed it using SageMaker, right? We got Docker deployment without any Docker code. So some key takeaways for me. If you're going to be doing crowdsourcing, you have to be really, really careful on how you do it, especially if your task is not trivial. Because otherwise, you're not going to get any real value from it. Crowdsourcing itself obviously will have bugs, will have errors, and you're going to be limited to its quality. And if you don't, you can never build a model that's better than whatever accuracy they're getting. So try to hold vendor trials if you can. Don't look at just one vendor. And if you have any way of doing QA on those vendors, you should put in the time and effort to do it. We built, a small scale sample in-house. There are other ways to do this, but you have to have a way of measuring, the performance of these vendors if you're doing trials. You can build very efficient crawlers using Scrapy and Scrapy-D. You don't need to be looking outside of these really powerful Python packages. They are production grade, right? They are that good. You can build really powerful NLP models using pre-trained BERT and without much additional training. There are really, really nice wrappers from Hugging Face for PyTorch. I think TensorFlow has one as well. It works, right? It really, really does work without much addition to the native BERT. And you can train and deploy models on very powerful machines. At some point we were using 16 GPUs. And using SageMaker, and you don't need to know anything about Docker to do this, right? You can do it independently as a data scientist. And also, just a general note, we had many times here where we did not know what the outcome would be, and we basically crossed our fingers and really hoped that it would turn out. I suggest you do that as well, because it doesn't, let's say it's not very productive to get scared of the things that you don't know. It's really, I think it's best to roll the dice and just see what comes out. Usually you can cobble something together that does yield value. So that's it. That's it for me. I'm happy to take any questions if there. Okay, yeah.
Yeah, thank you for the talk. It was very interesting to see all the different parts. I was wondering, in the beginning you were talking about you made per page, you made an order at what rate you got it in, but you also made a ranking. Could you tell a bit more about that ranking, and if you used it, how you used it, or if you didn't use it, why it wasn't useful?
Yeah, the question was, what's the difference between the ranking and the order that we did, right? And how the order was the order in which we encountered the web pages, and the ranking was our own custom keyword-based thing, right? If we were trying to prioritize about us, services, those types of keywords. So our primary sort of ordering was using that, and then our secondary, because sometimes they get the same score, and then we have to tie break, and then we use the actual rank. Yeah.
On the third page, did you use any proxy or anything like that?
Okay, the question was, did we use proxies? No, but we used other things, but not proxies.
You need to protect yourself.
Yeah, I wouldn't run anything like this from your laptop. Yeah.
Did you benchmark your classifier more simple?
This was the simple approach. We actually tried some other stuff. Remember I mentioned that we concatenated it into one giant vector? So we tried doing things that were much more complex than that. We tried turning it into matrices and then doing a convolutional net on them with many, many different layers. We tried a whole bunch of things. This is the simple version. We also tried going 10 pages deep, 15 pages deep, 30 pages deep, and the marginal gains there were not that great. Yeah. Yeah. Question was, did we try without a GPU? Once, and I regret it already. I waited 40 minutes for nothing. I don't know how long it took because I gave up after 40 minutes. Yeah.
Does your model assign multiple labels or only single
one? It assigns multiple labels, but I've been asked a similar question before. I don't know if that's what you're asking. It assigns multiple labels in one pass, but we could have built it in a way. We could have built 135 single label models, and that might have been a bit better. I don't know if that's what you're going for. But this model is a multi-class model. Yeah?
Did you try to compress the vectors into one vector, like building the centroid out of this component concatenated vectors and just averaging the dimensions?
No, but that's a good idea.
It's a very good idea.
I know, I'm going to try it.
We did it in our company.
And did it work?
It compresses information into much more.
Yeah, that sounds like a good idea.
The second question is whether did you try using XGBoost instead of this neural network?
Yeah, we tried.
Because you're not really using graphics in the neural network.
Well, we are using, the question was, did we try to use XGBoost and not a learnable layer? We are using nonlinear activation in there, right? So with
XGBoost is running on CPUs, GPUs. It's much, I think it's faster, and it also it's better for in-balance data.
Yeah. No, we actually did try XGBoost, and we had overfitting issues with it. I honestly don't know how much of a real effort we gave to making XGBoost work. One of the reasons was that if you use the Hugging Face, the PyTorch Hugging Face thing, it's much easier to do that. It's very easy to apply just one layer. So even from a technical standpoint, it was just easier for us to approach it. And we're nowhere near done testing out variations of this. So we might very well go back and try that. But the honest answer is we gave it a go, a very half-assed go. It was overfitting, and we just moved back to the layer. That's just how it turned out. Yeah, you may be right. You might very well be right. Yeah.
What about using metadata? Like, first of all, if you are splitting your page in the text of any web page in full parts, you could add like a number to say it's the same page to differentiate. You could also add a position of the text, maybe, something like that. Is there
Yeah. The question was, are we using metadata from the pages, and are we thinking of splitting the page up into pieces? We're definitely looking into using HTML tags, right? I mentioned that we immediately stripped it all off. Our next step is going to be to go back and try to leverage that. Your idea about splitting the page up into pieces, I don't know that we need to, just because 512 captures most of the page, as one. We were thinking of perhaps trying to figure out specific frames inside the page, right? If you can focus on a frame that says something as opposed to other frames that say something less important. So maybe that's a bit what you were saying, trying to split up the page, not into sequential pieces, but maybe into logical pieces. But in terms of metadata that we're using today, it's limited to the website extension and the extension of the domain and the specific path, like the text path and the click text of the page. Yeah. Anyone from? Yeah.
I have a question about how you design to. It means you try different kind of sites, and you find that these are the right dimension for getting the high score, or you.
Which site?
It means when you do before the BERT model, when you tokenize with the BERT, and then you have a kind of vector with the site. You decide.
You're talking about are you asking how we decided how long to make each vector?
Yeah.
Okay, yeah. For the page length, we took the maximum, 512, that BERT could accommodate. For all the other ones, I think I mentioned this, we measured the distribution of the actual token lengths, and we took the 95th percentile. So our thinking was if you can get as much information as possible, you should get it. We did not test trying to go lower, right? I didn't check what happens if you take only the first 4 words or something like that, simply because it didn't seem to be that much of an issue. Like our issue was more how to avoid information loss. So 95th percentile works for everything except the full page. And 512, I think, turns out to be like the 80th percentile. So perhaps going to his question over there, we might be splitting pages up into pieces to accommodate more, but that's like next level complexity for us. So.
The second question, are you ranking then because I think you have like a list of possible output, right?
Yeah.
So how you rank there, based on just probability of the model?
Yeah, the question is how do we rank the output? The output is a vector size 135 of probabilities, and we take the top X, right, based on the likelihood. But it matters for us, remember I mentioned use cases in the beginning, right? For example, if we can't work with a gambling business. So if a gambling business is appearing in the top 3, we will treat that differently. It doesn't have to be the first one, right? Whereas for other contexts, we're going to be looking just at the top decision.
Even if they are almost the same meaning, we are not trying to get a similarity as well between the output.
Sorry, can you repeat that?
Kind of, you're not doing kind of similarity between the output as well. Means you are not trying to, or your output is already completely.
Yes, it's a vector of probabilities. Yeah, I'm not sure what you mean by.
Means that you're already using. Okay, no, I got the point.
Yeah, we can maybe do it after. Yeah.
Is it possible that you would encounter websites that are not in English? So, for example, a German customer that doesn't have an English website would apply?
Yeah, our company works with US-based customers as a default. But if you want to build this for a different language, BERT works, like pre-trained BERT versions exist for many, many languages. And this is one of the best models to be using for multilingual, right? So if you could generate a tagged set of German websites, you could recreate this entire thing.
You could combine them together and combine the information. Or would you translate it first with Google Translate or something?
I mean, if you translated with Google Translate, it probably would be good, but probably not great. I mean, it would be much better to use real German websites.
Two separate models, one for
Yeah.
each one.
Yeah, but for our purposes, it's a huge edge case to get a non-English website. I mean, from a regulatory standpoint, we work only with US businesses. Yeah. Any other question? Yeah.
Have you considered simplifying the problem by having higher level categories and then simpler model for separate?
Yes, we definitely considered that. I mentioned that briefly when I talked about crowdsourcing. It was really hard for us to get a quality sample that way. We tried generating a sample. There's about 20 high-level industries, and they filter down into the 135. And we could not get quality tags on the top. You would think it's an easier task, but it turned out not to be. So that was why we didn't build a model for that, because we could not generate a sample to model on, right? We could go back, given the lower level, and try to impute the higher level and generate a model, but I don't know if I don't know if that would help make a better model.
I think to the point of the previous
Yeah.
person, I think he was asking is if you have gambling, computing, and construction as the top three, then
Right.
it's not consistent. So do you trust the output of the model?
Oh, is that what you meant by similarity? Okay. Okay, those are great points. We have not checked anything like that yet, but those are really, really good suggestions. Thank you. From my experience just interacting with the model, it almost never happens. It's usually very, very focused on a few things that look very similar. But to qualify that, the model there's a certain subset of industries that it does not do well on as a rule. And there we see the problem that you described. But we're just not going to be using the model at all for those, right? For example, there is an industry called e-commerce. It just happens to be an industry, and it's super confusing because you have a website that sells clothes, but it's e-commerce, so it's thinking it's a wholesale clothes thing, and wholesale is completely different from e-commerce in our structure. So e-commerce is specifically an industry where we see this problem, but we've already decided not to use the model for that. It's a very small subset. It's under a single-digit amount of websites of industries that happens for. Yeah. I think we're done with questions. All right, cool. Thank you, guys.